There's a particular kind of quiet that happens late at night when you stop doing things. Not the absence of noise, there's always some noise. A radiator, a car on a wet street somewhere outside. But the quality of attention changes. The brain stops sorting and starts just receiving. I think that's part of why the bigger ideas in physics, the ones that should probably feel alarming, end up being easiest to absorb in the dark. The mind is already somewhere between here and not quite here, and the ideas just settle in. So, somewhere above you right now, if you're lying down, above you, if you're sitting ahead of you, behind the ceiling, behind the skid, behind the gas and the dust and the 26,000 light years of crowded galactic real estate, there is a centre, an actual centre. Not the centre of the universe, which doesn't have one, but the centre of this galaxy, your galaxy. And at that centre there is something with mass, real, stubborn, gravitationally consequential mass. That's where this is going. Before it does, this project runs on its own. No institution behind it, no network funding it. Just the work and the people on Patreon who make it possible to keep going. If you've ever felt like this kind of space is worth keeping alive, that's the place. It genuinely matters. I grew up thinking of the Milky Way as a picture, that smudge across certain skies, the ones dark enough to show it, which I didn't actually see until I was much older than I should have been. Cincinnati isn't exactly a dark sky destination. The first time I really saw it, properly saw it, I remember the feeling not being wonder so much as a kind of offence, that it had been there the whole time, that I'd been inside it the whole time and it had taken this long. The Milky Way is a barred spiral galaxy, around 100,000 light years across, give or take, 100 billion stars, though that number shifts depending on what you include in the count. And honestly, the uncertainty there is bigger than most astronomy communication lets on. A disk, roughly, with a central bulge and arms that trail outward in long, loosely wound curves. We sit about 26,000 light years from the centre. In galactic terms, that puts us somewhere in the suburbs, not the edge, not the middle. The kind of location where you're aware of the city without being in it. And that city has a centre. Every city does. Here is something that took me longer than I'd like to admit to really sit with. The Milky Way is not a loose collection of stars that happen to be near each other. It isn't like a crowd at a train station, all moving in their own directions for their own reasons, only coincidentally occupying the same space. It is a structure, an organised system. The stars move in particular ways, not randomly but in orbits, governed by the distribution of mass across the whole galaxy. And the centre of all that mass, the gravitational anchor around which the whole thing slowly wheels, is not empty. It never was. The Sun orbits the galactic centre. Takes about 225 million years to complete one full circuit, a period sometimes called a cosmic year. In the time since Earth formed, the solar system has made roughly 20 of those circuits. In the time since the dinosaurs went, less than one. The orbit is real, the gravitational influence driving it is real. And at the centre of it, sitting at the rotational heart of everything we can see from here, is Sagittarius, a star. Named, somewhat improbably, because the radio source was exciting, and excited states of atoms are marked with asterisks. So the most massive single object in the Milky Way got its name from an enthusiasm in notation. That still seems slightly wrong to me, or maybe it's just right in a way I haven't fully parsed. What does it mean for something to have mass? Not philosophically, physically. In everyday life, mass is the thing that makes objects heavy. the resistance you feel lifting something, the drag when you try to stop something moving. But at galactic scales, mass is something else. It's a geometry, a curvature in space. The heavier an object, the more the space around it bends toward it. And things caught in that bend don't fall. They orbit. They trace paths along the warped geometry the mass has created, and those paths hold. Sagittarius. A star is, as far as anyone can determine, a supermassive black hole. The designation supermassive is not hyperbole, it's a category. Black holes come in a range of sizes. Stellar mass black holes form when large stars collapse at the end of their lives. 10, 20, maybe 50 times the mass of the Sun. Then there's a gap, somewhat puzzling, and then there are the supermassive ones, millions or billions of solar masses, sitting at the centres of most large galaxies. The mechanism by which they grow that large is still not fully resolved. That might be the honest way to say it. Sagittarius. A star sits at the lower end of the supermassive range. It contains roughly 4 million times the mass of the Sun, maybe 4.297 million, according to the most precise current measurements, though even that number carries an uncertainty of around 10,000 solar masses, which sounds enormous until you remember the number it's attached to. As a fraction of the total, the uncertainty is tiny. The mass itself is not. 4 million solar masses. I want to stay here for a moment because the number doesn't land the way it should on first contact. The brain takes 4 million and files it under large number, moves on, but the Sun is already almost incomprehensible. 1.4 million kilometers across, 330,000 times the mass of Earth, a thermonuclear reactor that has been burning for 4.6 billion years and has enough fuel left for another 5 billion or so. The Sun is not a modest object. And Sagittarius. A star contains 4 million of them, compressed, present, actually there. The event horizon, the boundary beyond which nothing returns, has a radius of about 12 million kilometers. The diameter, roughly 25 million kilometers. That sounds enormous, but hold it next to the solar system. Mercury orbits the Sun at about 58 million kilometers. So the entire event horizon of Sagittarius, a star, fits inside Mercury's orbit, with room left over. A 4 million solar mass object, and you could draw a circle around it that Mercury's path wouldn't cross. That's not small. Nothing about this is small. But it means the density implied is extraordinary. All of that mass packed into something that would fit neatly inside the inner solar system. The compression involved defies any ordinary intuition about how matter is supposed to behave, and it does this quietly, without moving, just sitting at the centre, being massive, bending the space around it in ways that propagate outward across 26,000 light-years and reach eventually the unremarkable corner of the galaxy where the Sun makes its slow, patient circuit. There's a metaphor I keep coming back to, and I want to be careful with it, because it doesn't hold perfectly. But imagine a very large piece of fabric stretched flat. Place a heavy object in the middle. The fabric dips. Things placed on the surface nearby begin to slide towards the depression, or if they have enough sideways velocity, they begin to orbit it. The depression, the curvature, spreads outward across the fabric, and even at some distance from the center object, the fabric is no longer flat. That metaphor is the rubber sheet model of general relativity, and physicists cringe at it rightly, because space is not a fabric and gravity is not a dip you can see. But the part of it that I find useful is this: the influence is not local. The curvature doesn't stop at some defined boundary and then simply return to flat. It extends. It thins as distance increases, falls off as the square of the distance, but it doesn't vanish. Sagittarius. A star 26,000 light-years away contributes to the gravitational environment of this solar system. Not dominantly, the Sun dominates here, and the combined mass of the rest of the galaxy plays a much larger role in our orbit than Sagittarius a star does alone. But the centre is felt. The whole structure is felt. The fact that Earth orbits the Sun, and the Sun orbits the galactic centre, and the galactic centre has this particular mass at its core. These are not separate facts. They are one connected architecture, and Sagittarius a star is the anchor at the deep end of it. What the chapter hasn't done yet, what it isn't going to do, not tonight, is explain how Sagittarius a star got there, or what it does to things that come too close, or what it was doing 3 million years ago that left marks on the galaxy that are still expanding as you listen to this. Those are real questions with real answers, or at least real attempts at answers. They'll come. For now, there's just the weight of knowing it's there, at the centre, sitting in the middle of everything you've ever been part of, without announcing itself, without doing anything particularly dramatic from our vantage point, just being massive, holding the structure together the way that quiet, stubborn things sometimes hold structures together. There is something at the centre of the galaxy, and it has been there, in some form, through various stages of its growth and activity and long stretches of relative dormancy, for longer than the Sun has existed. That's where the next part begins. 4 million solar masses. Put it down like that, just the phrase, nothing attached to it, and it doesn't do anything. It sits there. The brain reads it, acknowledges it, and sort of nods the way it nods at any sufficiently large number. 4 million. Sure, fine. The brain is not built for this. It was built for predators and weather and the distance between two trees, and it has spent most of human history dealing with quantities that fit inside the double digits. 4 million solar masses is not a quantity the brain was ever asked to handle, and it shows. So let's try something else. The Sun. Start there, because at least the Sun is something. The Sun is 1.4 million kilometres across. If you drove a car at highway speed, call it 100 kilometres an hour, from one side to the other, it would take you about 1,600 years. It contains 99.86% of all the mass in the solar system. Every planet, every moon, every asteroid, every comet, every scattered piece of rock and ice out past Neptune, all of that together makes up the remaining 0.14%. Jupiter, the largest planet, is about 1,000th of the Sun's mass. Earth is about 3 millionths. The Sun is not a modest object. The Sun, in the context of Sagittarius a star, is a unit of measurement. That's the shift that needs to happen. The Sun stops being a vast, incomprehensible thing and becomes instead the base unit, the one in a different counting system. And in that system, Sagittarius a star counts to 4 million. I wrote that number out once just to see it. 4 million solar masses. And then, because I was curious and slightly deranged that particular afternoon, I wrote out what one solar mass is in kilograms. The Sun weighs, if weighs is even a word you can use here, approximately 2 times 10 to the 30th power kilograms. 2 followed by 30 zeros. Multiply that by 4 million and you get 8 times 10 to the 36th power kilograms. 8 followed by 36 zeros. I stared at it for a while. The number didn't become more real. It became, if anything, more abstract, the way a word stops meaning anything if you say it enough times. I stopped writing and made coffee instead, which at least had a comprehensible mass. The honest answer is that these numbers resist imaging. Not because we're not smart enough, but because there is nothing in human experience that maps onto them. You can get close to understanding what a million of something looks like. A stadium full of people maybe, or the dots on 1,000 pages of text. But 4 million solar masses involves two separate incomprehensible quantities multiplied together, and the result is something that exists only as notation, as a claim about the universe that you either accept or you don't. I accept it. The evidence is overwhelming and we'll get to some of it. But I want to be clear, accepting it is different from holding it. And holding it is what this chapter is actually about. Here is one way to approach the size: Sagittarius. A star has an event horizon, the boundary of no return, with a radius of roughly 12 million kilometers. The diameter, therefore, about 25 million kilometers. 25 million. That's the physical extent of the thing, more or less. To the degree that physical extent means anything for a black hole, which is, well, that's its own complicated conversation. 25 million kilometers sounds large. And then, Mercury orbits the Sun at an average distance of about 58 million kilometers. So the event horizon of Sagittarius, a star, all 4 million solar masses of it fits inside Mercury's orbit. Not just fits with space left over on both sides. You could draw a circle at Mercury's distance and the entire event horizon would be comfortably inside it, the way a marble sits inside a salad bowl. And that's, I almost said surprisingly small and then caught myself because it isn't small, nothing about it is small, but it is smaller than I instinctively expected. The density implied is almost worse than the mass. All of that, 4 million solar masses, crammed into something geometrically comparable to a small corner of the inner solar system. The compression is the thing that actually gets to me. Not the mass alone, the mass and the size together held in the same thought. Astronomers have been measuring Sagittarius, a star's mass, for decades. The method, at its core, is something almost classical. Watch things orbit it, and use the geometry of those orbits to infer the mass at the centre. Kepler's laws, applied at galactic scales. You measure the period of the orbit, the size of the orbit, and the math tells you what's pulling. The stars that make this possible are called the S-stars. A cluster of them, orbiting Sagittarius, a star, at distances close enough that their orbital periods are measured in years, not thousands of years, not millions years. The star S2, sometimes called S0-2, depending on which research group is naming it, completes a full orbit in approximately 16 years. 16 years. It moves at up to 7,650 kilometers per second, near its closest approach to the black hole, about 2.5% of the speed of light. At those speeds and that proximity, general relativistic effects become detectable, gravitational redshift, orbital precession, and the observations become a test of Einstein's equations as much as a measurement of mass. Two independent research groups, one in Germany at the Max Planck Institute, one in the United States, spent decades monitoring those stars. They got slightly different values, as measurements do. The German group found roughly 4.31 million solar masses. The American group 4.1 million, with a slightly larger uncertainty. The current best estimate pulls everything together and lands at 4.297 million solar masses, with an uncertainty of about 12,000 solar masses. 12,000 solar masses of uncertainty, which is itself 12,000 times the mass of the Sun. The error bar, if you pulled it out of context, would be the most massive thing in the solar system by a factor of 12,000. And in the context of the measurement, it's a rounding detail. There's a particular thing that happens when you try to compare Sagittarius, a star, to something more familiar, something with emotional weight, and it doesn't work. I started to write a sentence that compared it to a mountain, then realized the comparison was so many orders of magnitude off, it was essentially fiction. I thought about comparing it to all the water in Earth's oceans. also fiction. The human world, the physical world of objects you can lift, structures you can walk around, even geological features that take your breath away, is simply not the right register for this. The mountain doesn't help. The ocean doesn't help. Even the solar system, which feels vast, only barely helps. What does help a little is time, not as a comparison, but as a frame. The sun has been burning for 4.6 billion years. Sagittarius, a star, or whatever concentration of mass preceded its current form, has been accumulating at the center of the Milky Way for longer. The galaxy itself is around 13.5 billion years old. The supermassive black hole at its center is thought to have grown progressively over that time, pulling in gas, disrupting and consuming stars, occasionally merging with other massive objects. 4 million solar masses is not a thing that appeared suddenly. It is the slow, stubborn accumulation of billions of years of gravitational inevitability. The mass is almost like sediment, not in what it's made of, but in how it got there. Layer after layer after layer, over a span of time that makes the existence of Earth look like an afterthought. That framing doesn't make the number easier to picture, but it does make it feel less arbitrary, less like a fact that arrived from nowhere. The Event Horizon Telescope released the first image of Sagittarius, a star, in May 2022. It looks, in that image, like a blurred orange ring surrounding a dark center. The bright ring of hot lensed gas, the shadow of the event horizon itself. The image took years to produce. It required a planet-spanning network of radio observatories linked into a single Earth-size virtual telescope, petabytes of data, and algorithms that could reconstruct an image from incomplete information. The resolution required was equivalent to photographing a golf ball on the moon from Earth's surface. The image is not sharp, it can't be, given the physics of the wavelengths involved and the dust between us and the galactic center. But it is real. It is an actual image of the region around an actual 4 million solar mass object 26,000 light-years from here. The blur is real, the ring is real, the dark patch at the center, the shadow of something from which light cannot return. That's real too. I find it hard to look at for too long, not because it's disturbing exactly, more because it refuses to look as significant as it is. A fuzzy orange ring, the mind wants something more visually commensurate with the mass it represents, and instead it gets the modest, slightly smeared circle of light. 4 million solar masses, and the most direct image we have of it looks like a photograph taken through a fogged window. There's something almost fitting about that. The number hasn't gotten easier to hold by the end of this. I want to be straight about that. I don't think that's how it works. 4 million solar masses is going to keep being 4 million solar masses, and the brain is going to keep filing it under large without really digesting it. What changes, maybe, is the texture around it, the orbital periods of the S-stars, the event horizon fitting inside Mercury's orbit, the 360 number sitting on a piece of paper that still didn't feel like anything. The mass is real. The object is real. It's sitting at the center of the galaxy right now, not metaphorically, not as an abstraction, as an actual gravitational presence that the entire Milky Way is organized around, including the Sun, including here. That's the number, 4 million solar masses, give or take 12,000. What it does with that mass, what it has done, what it is quietly doing right now without much fanfare, is a different kind of question, and it starts somewhere much closer to the present. Sagittarius. A star is not doing much right now. That sentence took longer to write than it looks. Not because it's complicated, it isn't, but because the more I sat with it, the stranger it started to feel. Not doing much. A 4 million solar mass object at the center of the galaxy, and the accurate description of its current behavior is that it is not doing much. It accretes. That's the word. Matter falls toward it. Gas, dust, the occasional tendril of stellar wind shed by nearby massive stars. And Sagittarius, a star, pulls it in, but it does this at a rate so low by black hole standards that it produces almost no significant output. A few hundredths of an Earth mass per year. The luminosity this generates is roughly 100 billion times less than what you'd expect from a comparably massive black hole that was actively feeding. Astronomers have a term for this category of behavior. They call it radiatively inefficient. The mass is all there, the gravity is all there, the accretion is happening, but almost none of the energy that should theoretically be released actually gets released as radiation. It just doesn't come out. The machine runs at a fraction of its capacity, and has been doing so, as far as we can tell, for a very long time. There are flares, small ones, measured in infrared and X-ray. SGR A star produces them with some regularity, several per day sometimes. A clump of gas falls in at a slightly higher rate, or orbits briefly in the accretion flow and gets heated, and for minutes or hours the luminosity bumps upward by a factor of a few. Then it settles back. Astronomers watch these flares the way you might monitor a very old, very large animal's breathing. Not because each breath is dramatic, but because the pattern tells you something about the underlying state. The flares are not dangerous from here. They are not particularly dangerous from anywhere within a reasonable distance. The X-rays and infrared involved are real, but Sagittarius, a star at its current activity level, is not an energetic source by the standards of what it could be, by the standards of what it has been. Here is the thing about dormancy that I keep coming back to. It doesn't mean absence. A quiet black hole is still a black hole. The gravity doesn't pause. The event horizon doesn't retract. The stars of the S cluster, S2 and its companions, orbiting at fractions of a light year from the center, are still moving at thousands of kilometers per second along their tight ellipses, still losing a tiny amount of energy to gravitational wave emission on timescales too long to measure directly, still tracing the paths that Sagittarius A star's mass dictates. The quietness is not emptiness. It is more like, and I want to be careful here, because the comparison doesn't hold cleanly, it is more like the quietness of something very heavy sitting very still. The weight doesn't diminish with the stillness. If anything, the stillness makes it more present, not less. Current measurements put Sagittarius A star's accretion rate at something like 1/10,000th of a solar mass per year. Some estimates go lower. To put that in terms that at least have the shape of meaning, the Sun loses about 1/10 billionth of its mass each year through the solar wind. Sagittarius. A star is pulling in roughly 10 million times more material than that annually, and it's still considered quiet, still considered in the taxonomy of active galactic nuclei essentially switched off. The Milky Way is what's called a low-luminosity active galactic nucleus, LLAGN, or sometimes it's classified as a low-ionization nuclear emission region, depending on the epoch of observation and which team is doing the classifying. The terminology varies. What doesn't vary is the underlying situation. The central black hole of this galaxy is running well below capacity, and has been for, it's not entirely clear how long actually, millions of years almost certainly. The evidence for a more active past is written in structures that are still expanding outward above and below the galactic plane. But the current state has been the current state for long enough that it seems stable, at least on human timescales, at least on the timescales of recorded observation. There's something mildly unsettling about the phrase stable at current timescales, and I'm not going to pretend there isn't. The region immediately surrounding Sagittarius A star is not, despite the black hole's relative quietness, a calm place. the central molecular zone, the dense, turbulent region of gas and dust within the inner few hundred light-years of the galactic centre, is one of the most hostile environments in the Milky Way. Intense magnetic fields, extreme cosmic ray densities, violent stellar winds from the young massive stars that orbit within a fraction of a light-year of the black hole. The young nuclear star cluster, O-type stars and Wolf-Rayet stars, massive and short-lived, burning hot and fast, orbits within that innermost region. The fact that young stars exist there at all is itself a puzzle. The tidal forces that close to Sagittarius A should rip apart the gas clouds before they can collapse into stars. And yet stars formed, somehow. The galactic centre is loud and brutal and strange, and the black hole at its middle is, by its own standards, barely awake. I think the dormancy bothers me more than I expected it to. Not in any practical sense. The practical implications for Earth are essentially zero. But there is something about knowing that the object at the centre of everything we're orbiting is resting, I suppose, running so far below its potential output that the language used to describe it involves words like inefficient and quiescent and low luminosity. Those are not alarming words. They're almost bureaucratic, and maybe that's exactly what makes them strange to sit with. You expect the most massive thing in the galaxy to have a presence commensurate with its mass, and instead, what you get is a faint, irregular flicker in the infrared, a barely there radio signal, and a lot of math pointing at a very large number. The presence is there, the mass is all there, but the announcement of it, the energetic shout that other, more active black holes make across billions of light years, is missing, has been missing, for reasons not entirely understood. Sagittarius. A star is consuming available material at a rate orders of magnitude below what the models predict it should be capable of. Why? That question is genuinely open. The leading explanations involve the structure of the accretion flow, the idea that most of the material captured at larger radii gets blown back out in outflows before it can fall all the way to the event horizon. Observations with the Chandra X-ray Observatory showed that while material is being captured at the Bondi radius, something like 99% of it never actually makes it to the black hole. It gets heated, accelerated outward and lost. Only a thin trickle gets through. Where the rest goes, what it carries, what it does when it leaves, that's part of a much longer story. There is a specific kind of quiet that settles in very late at night when you've stopped expecting anything to happen. The waiting feeling drains out. You're not listening for a sound anymore. You're just present in the absence of one. I think about Sagittarius, a star sometimes in those moments. Not because it's comforting exactly, more because the scale of its stillness makes my own stillness feel like something it's in conversation with. 26,000 light-years of separation, and the thing at the centre is just sitting there, pulling in a few hundredths of an Earth mass per year, producing a flare or two, each one monitored by telescopes on a small planet in the galactic suburbs, each one subsiding back into the low background hum that is all Sagittarius a star currently chooses to offer the universe. Chooses is the wrong word, obviously. Black holes don't choose. But the dormancy feels deliberate in a way I can't entirely explain and don't entirely trust myself to explain. What we know is this: Sagittarius. A star was not always like this. The structures visible above and below the galactic plane, expanding, still warm with the energy that produced them, are the record of something that happened when the black hole was different, more active, eating faster, outputting more, pushing material out at velocities that carved enormous cavities in the surrounding gas. How long ago that was, and what ended it, and what would be required to start it again. Those questions are where this goes next. The silence has a history, and the history is still written on the sky, if you know which part of the electromagnetic spectrum to read it in. On a clear night, if you go outside and face south and let your eyes adjust, really adjust, the full 20 minutes it takes for the pupils to open all the way, you can find the constellation Sagittarius low on the horizon. From Ohio, it barely clears the tree line in summer. It looks to me at least less like an archer and more like a teapot. There's even a region where the steam would rise from the spout, a dense smudge of the Milky Way that marks roughly the direction of the galactic centre. You can't see Sagittarius, a star itself. You can't see anything within thousands of light years of it from here. There's too much dust between us and the galactic core, blocking visible light almost completely. But you can stand there. You can point yourself in that direction. And something about doing that, even knowing it's mostly symbolic, is different from not doing it. There are stars near Sagittarius, a star that orbit it the way planets orbit stars. Not metaphorically. Literally, closed elliptical orbits, measurable periods, Keplerian dynamics. A cluster of them, called the S stars, moving at velocities that have no equivalent anywhere in the outer galaxy. S2 is the most observed, the most documented, the one that over the course of decades of watching told us more about the mass at the centre than anything else. S2 is a young star, massive, blue, hot, what's classified as a B-type main sequence star. It has no particular reason to be where it is. Stars like S2 normally form in the calm outer regions of galaxies, in molecular clouds where gravity gently wins over pressure over millions of years. They do not form, as far as anyone can comfortably explain, within a fraction of a light year of a supermassive black hole where the tidal forces should shred any cloud before it gets dense enough to collapse. And yet S2 is there, has been there for somewhere around 6 million years by current estimates. How it got there, whether it formed in place somehow or formed further out and migrated inward, is genuinely unresolved. The S-star cluster is sometimes called the paradox of youth, which is one of those scientific names that lands exactly right. Young stars in a place where young stars have no obvious right to be. S2 orbits Sagittarius. A star every 16.05 years. Its orbit is a highly elongated ellipse, eccentricity of about 0.88, which means it swings from a farthest point of roughly 10 light days to a closest approach of about 120 astronomical units, 120 times the Earth-Sun distance. At that closest point, periapsis, it moves at approximately 7,650 kilometers per second, 2.5% of the speed of light. Fast enough that if you could watch it directly, the Doppler shift of its light would be visible as a colour change with the naked eye. It takes 16 years to complete one orbit. I find myself wanting to sit with that. 16 years. The Voyager probes have been travelling for nearly 50 years and haven't left the solar system's gravitational influence. A star is completing a full lap around a black hole in 16 years. The math is consistent. The mass of SGR-A star and the size of S2's orbit produce exactly that period, and Newton and Kepler and Einstein all agree on it. But consistent math doesn't make the velocity feel less, wrong somehow. Not wrong as in incorrect. Wrong as in against the grain of what motion is supposed to feel like. The observations that pin down S2's orbit, and through it, the mass of Sagittarius, a star, required decades of near-infrared imaging. Visible light doesn't reach us from the galactic centre. The dust absorbs it. But infrared wavelengths pass through more easily, and by the early 1990s, two groups had begun monitoring the stars within the central parsec, with instruments sharp enough to resolve individual stellar positions. The German group at the Max Planck Institute for Extraterrestrial Physics, led eventually by Reinhard Genzel, the American group at UCLA, led by Andrea Ghez. They worked in parallel, sometimes in competition, for 30 years. Both groups tracked S2 through multiple complete orbits. Both groups published mass estimates. Both groups found general relativity effects embedded in the orbital data, the gravitational redshift of S2's light as it approached SGRA star, the Schwarzschild precession of the orbit itself, the slow rotation of the ellipse over successive laps in a way that Newton alone cannot account for. In 2020, Genzel and Ghez shared the Nobel Prize in Physics for this work. Ghez was only the fourth woman to receive the Nobel Prize in Physics. What they were effectively doing with their telescopes and their decades of patience was running the largest laboratory test of general relativity ever attempted. The extreme gravity near SGR-A star, a gravity regime no other accessible object can provide, bent and shifted the light from S2 in ways that Einstein's equations predicted exactly. Every measured deviation from Newtonian expectation matched the general relativistic prediction. The agreement is not approximate, it's precise. There is something about that I find unexpectedly moving in an unshowy way. Two groups of people on a small planet in the suburbs of a spiral galaxy, spending their careers watching a single star move, and using that motion to confirm the equations a Swiss patent clerk worked out sitting at a desk in 1915. The star, the black hole, the equations, the telescopes, the planet, all of it connected in one long chain of inference. The chain holds. S2 is not the only S-star. There are dozens of them, catalogued with designations that reflect the order of their discovery more than any quality of the stars themselves. S1, S4, S8, S12, S13, S14, on through the higher numbers. Some have even shorter orbital periods than S2. S62 completes an orbit in roughly 9.9 years, and its closest approach brings it within 16 astronomical units of the black hole, closer than any other confirmed S-star. At periapsis, S62 is moving at speeds where relativistic effects are not subtle corrections but dominant features of the physics. The stars are real. That's what I keep coming back to. The stars are real objects. They have temperatures and luminosities and spectral types. They are burning hydrogen somewhere very close to a 4 million solar mass black hole, doing the unremarkable interior work of main sequence stars, fusing and radiating and losing stellar wind into the surrounding environment, and also orbiting, also tracing tight ellipses at several thousand kilometers per second, lapping the galactic center every decade or two. Both things at once, the ordinary stellar physics and the extraordinary gravitational environment. Neither cancels the other. There's something specifically strange about the fact that S2 completed an orbit in 2018, one that was watched, measured, analysed in real time by people with instruments on the ground, and that orbit took 16 years, and the star doesn't know it's being watched. Obviously, the star doesn't know anything, but the observation has this quality of intimacy, maybe. A 16-year watch. People who started monitoring S2 in 2002 saw it return to roughly the same orbital position by 2018. Some of them had been graduate students when the observation campaign began. By 2018, they had careers, students of their own. The star made one loop. Human lives moved an appreciable distance. The black hole at the center didn't change in any detectable way. I had written didn't change at all and then pulled back. Because Sagittarius, a star, does change, flares, accretes, varies at small scales, but the mass, the essential gravitational character of the things, the same during S2's 2018 periapsis as during the star's formation millions of years ago. That's the thing about mass at this scale. It doesn't oscillate. It doesn't have moods. It simply continues to be what it is. Looking towards Sagittarius on a summer night, low over the tree line, the teapot shape barely visible through the light pollution, I'm aware that in the direction of that constellation, 26,000 light-years behind the dust, a star is moving at thousands of kilometers per second along an ellipse that will bring it close to a black hole in a few years' time. The star has no opinion about this. The black hole has no opinion. The orbit continues, and there are dozens more like S2, all of them tracing their own paths, all of them observed at some point or another by people on a planet that is itself orbiting further out at a much more leisurely pace. Everything orbiting something, the nested circles of it, each one governed by the same underlying rules, each one telling you something about the mass at the centre if you watch long enough. 16 years. Some of the orbital periods are shorter, some are measured in decades, but they all converge on the same thing, the same mass, the same number, the same object sitting in the dark at the centre of the galaxy, being exactly as massive as it is, holding every orbit in place without any apparent effort. What it does with that gravitational reach, the structures it has built and wrecked and built again across millions of years, is something you can only see if you step back far enough to fit the whole history in the frame. Walk into a room where something significant has happened, and you will know before anyone tells you. The furniture is slightly off, the air hasn't settled. There are objects in places they wouldn't normally be, and an arrangement of details that doesn't quite add up to ordinary. You can't always name what happened, but the room tells you something did. The galaxy has rooms like that. Above and below the flat disk of the Milky Way, perpendicular to the plane where most of the stars and gas live, there are structures, enormous ones. The Fermi bubbles, discovered in 2010, when physicists combing through data from the Fermi Gamma Ray Space Telescope found 2 lobes of gamma ray emission rising symmetrically from the galactic center. Each bubble extends roughly 25,000 light-years. Together they span about half the diameter of the visible Milky Way. They are not faint. In gamma rays they are among the brightest structures in the sky, and for years after their discovery nobody was entirely certain what made them. The room was obvious. What had happened in it, that took longer. Then in 2020 came the Erisita bubbles. The Erisita Space Telescope, a German-Russian X-ray observatory launched in 2019, released its first Allsky survey and revealed something larger still. Enclosing the Fermi bubbles, extending even further above and below the galactic plane, 2 additional bubble structures glowing in X-ray light. Each Erisita bubble reaches roughly 45,000 to 50,000 light-years from the galactic center. Together they span nearly the full diameter of the Milky Way's stellar disk, puffing out above and below it like something exhaled slowly and enormously. So, nested structures. The Fermi bubbles inside the Erisita bubbles, both centered on the galactic center, both roughly symmetrical above and below the plane. The symmetry matters. It suggests a common origin, something that produced energy in both directions simultaneously, or very nearly so. Random stellar activity distributed across the disk doesn't produce symmetric structures. A single centrally located energetic event does. The centrally located energetic object in the Milky Way is Sagittarius, a star. The question of exactly when and how this happened is where the certainty starts softening. The best current evidence suggests that the jet activity responsible for the Erisita bubbles began around 2.6 million years ago and continued for roughly 100,000 years. The energy involved, and this is a number worth pausing at, is estimated at around 10 to the power of 56 ergs, which is meaningless without context. So, a typical supernova, the violent death of a massive star, releases around 10 to the power of 51 ergs of energy. The event that inflated the Erecita bubbles was roughly 100,000 times more energetic than a supernova, sustained over 100,000 years. Sagittarius. A star was not, during that period, the quiet, low-luminosity object it is today. It was consuming material at a rate 3 to 4 orders of magnitude higher than current levels. The accretion flow was different, denser, hotter, more efficient. And the excess energy went somewhere. It went up and down, perpendicular to the galactic plane, in the form of jets and outflows that pushed the surrounding gas outward at hundreds of kilometers per second. The bubbles are what that outward push looks like, 2.6 million years later. Still moving, still warm, still faintly glowing in X-rays and gamma rays detectable from 26,000 light years away, by a species that didn't exist yet when the event began. I want to be careful here because the timeline is easy to get wrong in a specific way. 2.6 million years ago is a long time. It's before modern humans. It predates Homo sapiens entirely. Early members of the genus Homo habilis possibly, were just beginning to use stone tools on a small planet in the outer suburbs of the same galaxy. The galactic center was erupting. The jets were active. The bubbles were inflating. And on Earth, something was learning to chip rocks. I'm not trying to make that connection carry more weight than it should. The eruption didn't cause the stone tools. The radiation didn't reach Earth in any meaningful form. 26,000 light years is a long way, and the intensity falls off with the square of the distance, and the galactic disk itself provides shielding. The events are not causally linked in any direction, but they were simultaneous. That's just true. The most energetic event in the Milky Way in recent geological time was happening while the earliest members of our genus were beginning their first tentative experiments with tools. Both things were real and occurring in the same galaxy at the same time, and the remnants of one of them are still visible while the descendants of the other are now mapping those remnants with space telescopes. That's not meaning, it's just simultaneity. But I find it difficult to be entirely neutral about it. The Fermi bubbles have a sharper boundary than you'd expect from a slow diffuse outflow. The edges are relatively clean, not perfectly sharp, but crisper than models of gradual stellar wind accumulation tend to produce. This crispness is one of the main arguments for an active jet from Sagittarius A rather than a slow cumulative push from star formation across the disk. Jets are collimated. They punch through the surrounding medium with more directed energy, and the structures they produce tend to have more defined edges. The debate isn't fully closed. Some researchers have argued for a star formation-driven origin, or a combination of mechanisms. There are models that reproduce the bubble morphology without invoking a SGA star jet. But the Erecita bubbles made the case for SGA star origin significantly stronger. The larger structures are almost impossible to explain with distributed star formation alone. The energy budget doesn't work, the symmetry doesn't work, the geometry points back to the center. And at the center, there is only one object with the energy budget to have done this. There is a specific visual I keep returning to when I think about the Fermi and Erecita bubbles. Not an image exactly, more like a spatial fact that I have to construct each time, because it doesn't fit naturally into any frame I already have. The Milky Way's stellar disk, roughly 100,000 light-years across, maybe 1,000 light-years thick in our neighborhood. A flat structure, enormously wide relative to its depth. And above and below that flat structure, these two pairs of nested bubbles, ballooning out to distances of 25,000 and 50,000 light-years respectively. From outside, if there were something outside capable of seeing in X-rays and gamma rays, the Milky Way would look less like a simple spiral and more like a spiral with two enormous glowing spheres pushing out above and below it. The bubbles are larger than the disk is thick by a factor of, well, by a factor that makes thicker than it is wide, not quite the right phrase, but gesturing in that direction. They're vast in the dimension where the galaxy is narrow. They push into the galactic halo, the diffuse outer region of hot gas and dark matter that surrounds the disk. They are altering that environment as they expand, pushing halo gas outward, mixing temperatures, changing the conditions in the circumgalactic medium in ways that have long-term consequences for the galaxy's ability to form new stars. A thing, Sagittarius. A star did 2.6 million years ago is still, right now, changing the environment of the galaxy. The structures are still expanding, that's worth saying plainly, without anything attached to it. The Erecita bubbles are not static. They are moving outward into the galactic halo at this moment, at hundreds of kilometers per second, driven by the pressure of the hot gas trapped inside them. The energy that Sagittarius A star released during its active period is still propagating outward. The event ended roughly 2.5 million years ago. By current estimates, SGR-A quieted down, the jets switched off, the accretion rate drops, and the structures it produced have been coasting outward ever since, carrying that ancient energy through the halo. In another few 100 million years, they will have diffused enough to become indistinguishable from the background. The halo will have absorbed them. There will be no visible record of what Sagittarius A did, but right now they are still there, still moving, still warm with the memory of it. The chapter doesn't have a clean ending because the structures don't have one. They're mid-process. The bubbles are caught in the act of expanding the way ripples on water are caught between the dropped stone and the shore. The stone dropped 2.6 million years ago. The ripples are still crossing the pond. What they passed through on their way, what the radiation from Sagittarius A star's active phase did to the planets and atmospheres in the inner galaxy, and faintly, very faintly to this one, is something the next part moves toward. Not toward catastrophe, toward contact. The quieter version of what it means to be 26,000 light years from something that, for 100,000 years, was not quiet at all. 2.5 million years ago, the atmosphere above Earth looked, from space the way it looks now, thin, blue at the edges during daylight, dark and transparent at night. A layer so shallow relative to the planet's diameter that astronauts describe the shock of seeing it, this fragile skin, barely there, the only thing between the surface and everything else. The ozone sat where it sits now, roughly 15 to 35 kilometers up, a loose chemical arrangement of 3 oxygen atoms that absorbs incoming ultraviolet radiation with an efficiency that makes life on land possible and which requires almost nothing dramatic to disrupt. The galactic center, at that same moment, 2.6 million years ago, was doing something it is not doing now. The jets were active, the accretion rate was high, Sagittarius. A star was pushing energy outward in 2 directions, perpendicular to the galactic plane, at luminosities that would have made the Milky Way's core briefly visible as a faint but distinct source to any sufficiently sensitive eye in a neighbouring galaxy. The X-ray and extreme ultraviolet output was orders of magnitude above current levels. That radiation travelled outward from the galactic centre at the speed of light, in all directions, including the direction of the solar system's position in the galactic disk. 26,000 light years is a long way. The intensity drops with the square of the distance, falls off hard and fast, and most of it is nothing by the time it gets anywhere near here. But some of it arrived. A fraction of a fraction. And what a fraction of the X-ray output of an active galactic nucleus does to the upper atmosphere of a small rocky planet is not nothing. The ionosphere is the part of the atmosphere that interacts most readily with high-energy radiation. It begins roughly 60 kilometers above the surface, higher than weather, higher than most of what we think of as the atmosphere in any practical sense, and extends upward several hundred kilometers before the gas becomes too thin to usefully discuss as a layer at all. The molecules there are sparse, but they're present, and when energetic photons, X-rays, extreme ultraviolet, pass through them, they knock electrons free. The gas becomes ionized. The ionized layer changes how radio waves propagate. It changes the electrical properties of the upper atmosphere, and in sufficient quantities, the chemistry propagates downward. Ionization products can catalyze reactions that deplete ozone. This mechanism, high-energy radiation from astrophysical sources ionizing the upper atmosphere and triggering ozone chemistry, is well established. It's the same mechanism invoked to explain potential effects of gamma-ray bursts on extinction events, the same basic physics behind solar flare impacts on radio communications. The radiation arrives, the ionosphere responds, and if the dose is high enough, the ozone layer feels it. A 2017 study published in the Astrophysical Journal modelled the potential effects of Sagittarius, a star's active phase, on the habitability of planets across the Milky Way. The results were not subtle for planets in the inner galaxy. Within a kiloparsec or so of the galactic centre, the X-ray and extreme UV flux during the peak AGN phase was high enough that terrestrial planets could lose atmospheric mass comparable to that of present-day Earth's entire atmosphere. Life near the centre would have had a hard time. At 26,000 light-years, our distance, the flux was much, much lower. The study found effects at this distance were real, but not extinction level. The ozone would have thinned. The UV reaching the surface would have increased. By how much and for how long, and what biological consequences followed from that? Those numbers carry genuine uncertainties that the models are upfront about. The Earth's magnetic field, the specific geometry of the irradiation relative to the planet's orientation, the state of the ozone at the time, all of these affect the outcome in ways that are hard to reconstruct across 2.6 million years. What the models agree on: something reached Earth. Something altered the upper atmosphere. The effect was not zero, and at that time, 2.6 million years ago, when the jets were running and the bubbles were still close to the centre, and the X-ray flux was at something near its peak, the genus Homo was beginning. Homo habilis appears in the fossil record at around 2.4 to 2.8 million years ago. The earliest stone tools, the Oldowan industry, date to roughly 2.6 million years ago. Early human ancestors, not yet what we'd recognise as fully human, but unambiguously in the lineage, were on the surface of a planet whose upper atmosphere was being quietly, measurably altered by radiation from an active galactic nucleus 26,000 light-years away. I've reread that sentence several times, and I'm still not sure how to hold it. Not because it implies anything specific, it doesn't. Or at least I can't responsibly claim it does. The CRA star activity didn't cause the emergence of Homo. The ozone thinning didn't drive bipedalism or tool use. These things were happening on entirely different causal tracks. The evolution of early humans was driven by climate shifts, habitat fragmentation, competitive pressures, the specific geography of the African rift, not by galactic centre irradiation. But they were simultaneous. The timeline simply overlaps. A species beginning, a black hole active, the same thin atmosphere above both. That's not a connection. It's just proximity in time, two things occupying the same era. I notice, though, that I keep coming back to it. The atmosphere at 2.6 million years ago was, and here is where the sentence wants to go somewhere I should be careful about, the same atmosphere, not chemically identical, obviously. The composition has drifted over geological time, and 2.6 million years ago sits within the Pleistocene, a period of glacial cycling CO2 fluctuations, shifting vegetation zones. The atmosphere was recognizably modern in broad strokes, but not in precise chemistry. The ozone layer existed. The ionosphere existed. Life on land had been adapting to the UV environment for hundreds of millions of years. What additional UV reached the surface during the years when SGRA star was most active is genuinely uncertain. Some models suggest an increase of a few percent in surface UV flux at Earth's distance. Others go higher. The uncertainty in the original accretion rate, how active was SGRA star at peak, exactly, propagates into the radiation output estimates, which propagate into the atmospheric effect estimates, and by the time you reach a specific number for surface UV increase at 26,000 light-years, you're several uncertain steps from the data. What I can say, the effect was not zero. What I can't responsibly say, what it did to anything living. There's a specific thing I find myself thinking about when this material sits with me long enough. Not about early humans, not about the ozone, but about the atmosphere itself, the way it exists as a physical layer, actual stuff, actual molecules, nitrogen mostly, then oxygen, then trace amounts of a dozen other gases arranged by density and chemistry into distinct regions, each one doing specific things. The troposphere where weather happens, the stratosphere where ozone lives, the mesosphere above that, cold and strange, the ionosphere beyond, sparse and electrically active. We live inside this, completely inside it, the way you live inside a building without usually thinking about the building. The air is just there, the ozone is just there, and somewhere in the upper reaches of that layer, above the weather, above most of where any human has ever physically been. Photons from the galactic center have been arriving for billions of years and interacting with the molecules they find there. Most of the time the interaction is negligible. Sagittarius. A star is quiet, and the X-ray flux at this distance from a quiet SGRA is low enough that the atmospheric effect is unmeasurable. But the atmosphere doesn't know that the source is usually quiet. It just responds to whatever arrives. And 2.6 million years ago, more arrived than usual. The upper air responded, the ozone adjusted, the chemistry shifted slightly for years or decades or centuries. The duration of the effect at Earth's distance is also model dependent, also uncertain. And then SGRA quieted down, the jets switched off, the flux dropped, the ozone recovered. The atmosphere settled back into whatever configuration it had been maintaining before, and continued, just continued. The thing the chapter keeps approaching and not quite touching is this. The relationship between here and there is not zero. It never was. The galactic center and this solar system are not isolated from each other. They are part of the same physical system, connected by gravity and radiation and the long-range consequences of energetic events. Most of the time the connection is so faint it is operationally zero. The background X-ray flux from SGRA at 26,000 light-years is not something that registers on any biological scale. But the connection exists, the channel is open. 2.5 million years ago, something significant moved through that channel. It reached the atmosphere felt it. Life below continued without knowing, which is, when you follow it far enough, the ordinary situation of every living thing on this planet. Embedded in systems too large to see, connected to events too distant to register, altered by forces too slow or too faint to notice. The galactic center acted. The atmosphere responded. The response is now gone. absorbed back into the long chemistry of air and light and time. What Sagittarius a star did next, what it is set up to do again, and when, and how much larger the channel might open, is something the geometry of the galaxy is already arranging for. Not soon, not on any timescale that intersects with anything human, but the arrangement is already in motion. Lie still for a moment, not as instruction, just as a thought. You're horizontal, or nearly so, and the planet beneath you is pulling you toward it with a force you've never once not felt. Since the first second you existed, gravity has been present. A constant, directionless seeming pressure that you only notice when something interrupts it, a step off a curb, a sudden drop in a plane, the brief weightlessness of a jump. The rest of the time it is simply the condition of being here. Background, structural, the thing that makes down a direction. That pull comes from mass, from the 6 times 10 to the 24th power kilograms of rock and iron and silicate beneath you, accumulated into a sphere 12,700 kilometers across, exerting a force across the distance between your body and its center. The distance matters. Gravity weakens with distance, falls off as the square of it, so the farther you are from a mass, the less you feel it. But you never stop feeling it. The Sun is 150 million kilometers away. Its gravity holds Earth in orbit, not dragging it inward, but curving its path continuously, bending what would otherwise be a straight line into a closed ellipse. The Sun doesn't touch Earth. There is nothing between them but vacuum and the occasional photon. And yet the connection is constant, uninterrupted, operating across 150 million kilometers of nothing with perfect fidelity. Sagittarius. A star is 26,000 light-years away. 1 light-year is roughly 9.46 trillion kilometers. Multiply that by 26,000 and the number stops being a number in any useful sense. It becomes a placeholder, a label for a distance that has no human referent. I could write it out, 2.46 times 10 to the 17th power kilometers, and the notation is accurate, but it doesn't land. It doesn't produce the sensation of distance. It produces the sensation of a very large exponent. Here is the thing about gravity at these scales, the thing that took me longer than it should have to really absorb. It doesn't care about the distance. That's not quite right, actually. Let me come at it differently. Gravity weakens with distance, yes. The force from Sagittarius. A star at 26,000 light-years is incomparably smaller than the force from the Sun at 150 million kilometers. Direct gravitational pull from Escar A star on Earth is not measurable by any instrument we have. It is lost entirely in the overwhelming local influence of the Sun and the galaxy's distributed mass. In that sense, Sagittarius A star does not pull on you. Not in any way you could detect. But the Sun orbits Sagittarius A star. Or more precisely, the Sun orbits the galactic center, and the galactic center is where Sagittarius A star is, and the mass of Sagittarius A star is part of the mass that the Sun is orbiting. The orbit of the solar system around the galaxy, 225 million years per circuit, 220 kilometers per second tangential velocity, a path that has carried Earth around the galactic center roughly 20 times since the planet formed. That orbit is organized around the gravitational structure of the entire Milky Way, with the central mass as its anchor. Remove Sagittarius A star from the equation and the orbit changes. Not catastrophically. The black hole is 4 million solar masses in a galaxy of hundreds of billions of solar masses, and its fractional contribution to the total gravitational budget of the Milky Way is not dominant, but it contributes. Its mass is part of the geometry. Far stops meaning disconnected. That's the thing. At human scales, far means out of reach. The village on the other side of the mountain is far, and that distance has practical consequence. It takes time to cross, energy, intention. Farness and disconnection track each other reasonably well. But at galactic scales they come apart. Something can be 26,000 light-years away and still be structurally integrated into the system you inhabit, still contributing mass to the gravitational geometry that defines your orbit, still shaping in some fractional way the path the planet takes through the galaxy. The connection isn't strong, it isn't direct, it doesn't override the local physics, but it's real. The geometry of space in the solar system's neighbourhood is not quite the same geometry it would be if Sagittarius a star weren't there. The difference is tiny, unmeasurably tiny, practically speaking, but the difference exists, which means the connection exists, which means the concept of far is doing something more complicated here than it usually does. I used to think of the solar system and the galactic centre as separate things, the same way you might think of your house and a city you've never visited as separate things, both real, both in the world, but not in any meaningful contact with each other. That intuition is wrong, not dramatically wrong, not wrong in a way that changes anything practical, but structurally wrong. The solar system is not a closed environment. It is embedded in the Milky Way's gravitational field the way a stone is embedded in a riverbed. Held in place by the surrounding structure, oriented by it, its position and motion partly determined by forces originating far outside its own immediate neighbourhood. Sagittarius. A star is part of that surrounding structure. It has been part of it for the entire existence of the solar system. For 4.6 billion years, while Earth was forming and cooling and developing oceans and generating life, the mass at the galactic centre was part of the gravitational context in which all of that happened. Not the dominant context, not even a particularly significant one in terms of direct force, but present, continuously, unremarkably, structurally present. Lie still. The planet pulls you down with the force of 6 times 10 to the 24th power kilograms of mass beneath you. The Sun holds the planet in orbit from 150 million kilometers away. The galaxy holds the Sun in orbit from 26,000 light-years away. And at the center of that galactic gravitational structure, anchoring the whole nested arrangement from the inside out, is a 4 million solar mass object that is not doing anything dramatic today. It doesn't need to. The mass is enough. The geometry it creates, the gentle, persistent curvature of space extending outward from the galactic center through 26,000 light-years of gas and dark matter and scattered stars, is enough. You feel it in the sense that you are part of a system it organizes, not directly, not personally, but the path this planet takes through the galaxy, the slow 200 million year circuit that it has been making since before complex life existed on its surface, traces the edge of a gravitational well that Sagittarius a star sits at the bottom of. That's not distance, that's something else, something the word distance wasn't built to describe. Hold your hand up toward a light source, a lamp, a window, the glow of a screen in a dark room. What reaches your skin is electromagnetic radiation. Photons that left their source travelled through air and arrived. The air didn't stop them. It filtered some wavelengths, scattered others, let most of the visible spectrum through without interference. Your hand absorbs some of it as heat. The process is so ordinary that calling it a process feels like an overstatement. It's just light. It's just warmth. It's just what happens when you put your hand near something bright. Radiation from space works the same way at the physical level. Photons leave a source, travel through vacuum, arrive at the atmosphere, and the atmosphere decides what to do with them. Most of the time, for most wavelengths, the atmosphere handles it. Visible light gets through, that's why you can see the sky. Infrared arrives in quantities that warm the surface, but the higher energy stuff, X-rays, extreme ultraviolet, gamma rays, the atmosphere absorbs almost completely high up before it reaches anything living. The molecules in the upper air take the hit. They ionize, dissociate, re-emit in lower energy forms. The surface below remains largely unaware. The atmosphere has been doing this for billions of years. It is, among other things, a radiation management system. A passive one, operating without intention, but effective in the way that things shaped by billions of years of physical chemistry tend to be effective. It intercepts, it converts, it remembers, in a chemical sense, everything that arrives. Ozone. 3 oxygen atoms bonded in an arrangement that is, by molecular standards, slightly unstable, which is exactly what makes it useful. O3 sits primarily in the stratosphere, between roughly 15 and 35 kilometers altitude. The layer is not dense. If you compressed all the ozone in Earth's atmosphere to standard surface pressure, it would be a layer about 3 millimeters thick. 3 millimeters of gas spread across the entire planet, and it absorbs nearly all the incoming ultraviolet B and ultraviolet C radiation from the sun. The geometry of the absorption is almost improbably efficient. Just enough ozone at just the right altitude, doing just enough work. What disrupts it is chemistry. Specifically, what disrupts it is the introduction of reactive molecules that participate in catalytic cycles, chains of reactions that consume ozone without consuming the catalyst. Chlorine does this, bromine does it, and free electrons and nitric oxide produced by ionization of the upper atmosphere can do it too, given sufficient ionization intensity. This is the pathway. Not a dramatic one, not a sudden collapse, a catalytic thinning driven by chemistry, caused by ionization, caused by high-energy radiation arriving from outside. The question for Sagittarius, a star's active period, is how much ionization was delivered to Earth's upper atmosphere at a distance of 26,000 light-years, and whether that ionization was sufficient to drive meaningful ozone depletion at the surface. The modelling work is careful and explicit about its uncertainties. A 2017 paper, Balbi and Tombesi, published in Scientific Reports, estimated the X-ray and extreme ultraviolet flux reaching Earth during Cygnus A star's peak AGN phase. They worked from estimates of the peak accretion rate, translated those into luminosity, counted for the distance and the geometry of the galactic disk, and calculated the arriving flux. Then they modelled the atmospheric response. What they found for Earth at its current galactic distance was this. The upper atmosphere would have experienced significantly elevated ionization rates during the peak of the AGN phase. The surface UV flux, the UV actually reaching the ground, would have increased. By how much is where the uncertainties compound. The range in their estimates spans from modest increases to something more substantial, depending on assumptions about the peak luminosity and the duration of the most intense phase. The mid-range estimates suggest surface UV increases of several percent to perhaps a few tens of percent above baseline. Several percent doesn't sound like much, but the baseline UV environment is already at the edge of what many organisms tolerate. DNA absorbs UVB efficiently. The photochemical damage accumulates. A 10% increase in UVB at the surface is not invisible to biology. It shows up in mutation rates, in the vulnerability of surface-dwelling organisms, in the productivity of phytoplankton in the upper ocean, which anchor marine food chains in ways that ripple upward through every trophic level. A 10% increase sustained for decades or centuries is a different environment. Not an apocalyptic one, not an extinction level one at Earth's distance, but a different one, 2.6 million years ago. I keep returning to the timeline not to make it mean something it doesn't, but because the specificity of it does something to the abstraction. This isn't a modelled scenario for a hypothetical planet. This is Earth. This atmosphere. The same one. The ozone that thinned, if it thinned, was the same chemical layer that exists now at 15 to 35 kilometres altitude, doing the same job it has always done. What was living on the surface at that time? Early hominins, Homo habilis beginning to appear in the fossil record, along with the full Pliocene and early Pleistocene fauna, grasslands expanding across Africa as the climate shifted. None of it was aware of the source of the UV environment it was adapting to. Evolution doesn't require awareness of selective pressure. The organisms adapted to whatever the environment was. If the UV was elevated, that was simply the environment. If the ozone had thinned, the surface organisms had no reference for what normal looked like. They just lived in it. That's the strange part. And I'm not sure I'm describing it correctly. Let me try again. The strangeness is not that organisms suffered. It's that the environment was being shaped by something 26,000 light-years away, and nothing on the surface had any mechanism to know that. The atmosphere received the radiation. The chemistry responded. The UV changed. Life below adapted to the changed UV or didn't, and the selection pressure was indistinguishable from any other selection pressure. The galactic origin of it was invisible, completely invisible, all the way down. There's a particular quality to sunlight on skin in the early morning before the day gets fully underway. A low-angle warmth that feels different from midday sun, more lateral, less direct. That warmth is radiation from the sun, arriving through a longer atmospheric path, more of the high-energy wavelengths filtered out by the oblique angle through the air. The atmosphere is doing its work in a way that you can feel as a difference in quality, in texture almost, even if you're not thinking about it in those terms. I think about this when I think about what the atmosphere does with everything that arrives from space. It filters, it absorbs, it converts high-energy photons into heat, into chemical reactions, into altered molecular arrangements at altitudes where nothing lives. And it does this constantly for every source: the sun, the cosmic ray background, the faint X-ray flux of distant astrophysical objects, the slightly less faint X-ray flux of Sagittarius, a star, when it was active. The surface doesn't see most of it. The surface sees the result, the UV environment, the temperature, the chemistry of the air, but not the process, not the original signal. The atmosphere intercepts, processes, and delivers a transformed version of whatever arrived. In that sense, the atmosphere remembers everything. It carries the chemical record of every radiation environment it has ever processed. The ozone that thinned 2.6 million years ago and then recovered, that event left no obvious geological trace. No layer in the sediment, no chemical signature you could point to with confidence and say, this is where the galactic center touched us. But the process happened. The chemistry ran, the air changed, however slightly, and then changed back. The recovery matters, actually. When Sagittarius, a star, quieted, when the jet switched off and the accretion rate dropped and the X-ray flux fell back toward current levels, the ionization source diminished. The catalytic ozone depletion slowed. The ozone layer, given time, replenished. The atmosphere does this. It has a resilience built in by the same billions of years of chemistry that gave it its current structure. It can absorb a perturbation, and return to something like its prior state. If the perturbation doesn't exceed certain thresholds and the recovery time is available. Earth was at 26,000 light-years. The perturbation was real but moderate. The threshold was not exceeded. The recovery happened. And then the atmosphere continued, doing what it has always done, filtering, absorbing, managing the radiation environment of the surface, protecting the chemistry of life from the full energetic spectrum of the universe with a patience that doesn't require intention. The sunlight that reaches your skin has been processed by that same layer, arrives transformed, arrives at a level that skin can accept, that eyes can tolerate, that the chemistry of surface life is built around. The galactic center, when it was active, briefly altered what that layer transmitted. The alteration is gone, the recovery is complete. But the channel through which it happened is still there, still open. The same physical pathway between the galactic center and the upper atmosphere that has existed for as long as both have existed. Right now, almost nothing moves through it. Almost. There is a shape to the Milky Way that nobody alive has ever seen. Not because it's hidden exactly, because we're inside it. We sit roughly 26,000 light-years from the center, embedded in the disk, surrounded by gas and stars and dust in every direction, and trying to determine the overall shape of the galaxy from this position is something like trying to determine the floor plan of a building while standing inside one of its walls. The evidence comes indirectly from the distribution of radio emission, from stellar velocities mapped across the sky, from the positions of molecular clouds and HY regions, and the parallax measurements of masers scattered across the disk. From all of this, a picture has been assembled. It is a picture assembled from the inside from partial information, with significant uncertainties still in the details. What astronomers broadly agree on: the Milky Way is a barred spiral galaxy. A central bar of stars, elongated and dense, oriented at some angle to our line of sight. Estimates of the bar's length range from about 3 to 5 kiloparsecs, depending on the method and the epoch of the measurement, and the orientation is not perfectly constrained. Extending from the ends of the bar, 2 primary spiral arms, the Scutum Centaurus arm and the Perseus arm, and 2 or more secondary or partial arms, depending on how you interpret the evidence. The Sun sits in or near one of these partial arm structures, the Orion spur, a relatively modest feature between the 2 primary arms. The whole thing is rotating, not as a solid body. Different parts of the disk orbit at different speeds, with the inner regions generally faster and the outer regions slower, though the rotation curve flattens in a way that implies enormous amounts of unseen mass in the outer halo, which is a different problem entirely. The spiral arms are not fixed structures that rotate with the disk. They are density waves, patterns of enhanced star formation and stellar density that move through the disk at their own rate, slower than the stars themselves. The stars pass through the arms persist. It is a complicated object, more complicated than most images of it suggest. Sagittarius. A star sits at the center of the bar. At the center of the bar, at the center of the bulge, at the dynamical center of the entire rotating system. Its mass alone does not account for the rotation of the galaxy. 4 million solar masses is genuinely small relative to the hundreds of billions of solar masses in the disk and the vastly larger dark matter halo. But its position matters. It marks the center. It anchors the innermost gravitational environment, and the bar itself, that elongated stellar overdensity stretching outward from the central region, is partly a consequence of the gravitational dynamics of that center. Bars form in disk galaxies through instabilities. The disk, left to its own devices, doesn't stay smooth. Small perturbations amplify through gravitational feedback, stars get pulled into elongated orbits aligned with a common axis, and over time, hundreds of millions of years typically, a bar crystallizes out of what was previously a more axially symmetric structure. The central mass concentration influences how bars form and how long they persist. A too large central mass can suppress bar formation, a too small one fails to anchor it. Sagittarius. A star's mass, in the context of the Milky Way's overall structure, sits in a range compatible with the bar that exists. That's a careful way of saying the bar might look different if the central black hole were different, or might not have formed at all. The relationship is not simple and the models don't fully agree, but the centre and the large-scale structure are not independent. The spiral arms are harder to connect directly to Sagittarius, a star. Spiral structure in disk galaxies is driven by many things: tidal interactions with neighbouring galaxies, internal instabilities, the passage of the bar's gravitational influence through the disk. The Milky Way has had interactions, the Sagittarius dwarf galaxy, not Sagittarius. A star, a different object entirely. A small satellite galaxy has passed through the Milky Way's disk multiple times over the past few billion years, and simulations suggest those passages triggered waves of star formation and may have seeded or amplified the spiral arm structure. The Large Magellanic Cloud is doing something similar, more slowly, right now, so the spiral arms have multiple authors. Sagittarius, a star, is one contributor among several. Its gravitational influence at the centre shapes the dynamics of the bar, which affects the pattern of density waves propagating outward, which affects where stars form, which affects the appearance of the arms. The chain of causation is real but long, and by the time you get to the outer arms, the direct contribution of the central black hole is diluted through many layers of intervening dynamics. What Sagittarius, a star, does more directly and more dramatically is shape the inner galaxy, the central molecular zone, the nuclear disk, the distribution of molecular gas within the innermost few hundred light-years. These are directly governed by the gravitational and energetic environment of the central black hole. The gas doesn't just fall in, it accumulates in particular ways, streams along particular orbits, forms particular structures, determined by the combination of the bar's gravitational potential and the tidal field of the black hole. The inner galaxy has a specific architecture, and Sagittarius, a star, is the main architect of it. I want to be careful, actually. Architect implies intention, and there is no intention, but the word is useful in a structural sense. The way a river is the architect of a canyon, not through plan, but through sustained force applied over time, shaping the available material into a form that reflects the character of the force. Time, this is where the chapter has been heading without quite arriving. The spiral arms of the Milky Way didn't form quickly. The bar didn't snap into place. The rotation of the galaxy, the slow 225 million year circuit of the Sun around the centre, has been running for longer than complex life has existed on Earth. The galaxy's overall structure is the product of billions of years of gravitational interaction, stellar birth and death, gas dynamics, tidal forces from neighbours, and the slow accumulation of mass at the centre. Structure is not a thing the galaxy has. It is a thing the galaxy is continuously making at speeds too slow for any individual lifetime or any civilization's recorded history to observe directly. When you look at an image of a spiral galaxy, one of the nearby ones, Andromeda or the Triangulum or the Pinwheel, you are seeing a snapshot of a process. The image looks static. The arms look fixed like a design. They are not. The stars in those arms are moving through them, not with them. The arms themselves are drifting around the centre at their own rate, slower than the disk stars, so stars enter from one side, pass through the region of enhanced density and star formation, and exit from the other side over tens of millions of years. What looks like a fixed pattern is a wave moving through a medium of stars. A standing wave in a way, or not quite standing, more like a slow rotation of a density enhancement through a rotating disk. And the centre of all of it, the gravitational anchor that the wave patterns propagate around, the point toward which the bar is oriented, the bottom of the potential well that organises everything else, is where Sagittarius, a star, sits, has been sitting, for as long as the galaxy has been a galaxy. There is a specific difficulty in thinking about galactic timescales that I don't think gets acknowledged enough. It isn't just that the numbers are large, it's that the duration involved exceeds any intuitive framework by so many orders of magnitude that the imagination gives up and substitutes a feeling of largeness, which is not the same thing. 1,000,000 years feels big, 1,000,000,000 years feels bigger, 13 billion years feels about the same as 1,000,000,000 years if I'm honest. The intuition saturates. The numbers stop producing proportional responses. What I find more able, not more accurate, just more useful for sitting with the material, is to think about what has happened on Earth during one galactic orbit. One full circuit of the Sun around the galactic centre takes roughly 225 million years. In the most recent one, more or less, the dinosaurs went extinct, the mammals diversified, the continents reached something like their current configuration, the genus Homo appeared, developed language and fire and agriculture and all of recorded history. That all fits inside one galactic year. The Sun has completed about 20 of them since it formed. During those 20 circuits, Sagittarius, a star, has been at the centre, growing slowly, occasionally more active, occasionally less. The bar has been present. Bars form and can dissolve, but the Milky Way's bar appears to have been there for several billion years at least. The spiral arms have wound and rewound, the pattern shifting slowly, stars cycling through the density waves over and over. The structure persists, not because it is rigid, but because the forces that create it are continuously operating. The galaxy has a shape because it has a history. The shape is the history, written in the current positions and velocities of hundreds of billions of stars, and at the centre of that shape, organising the innermost dynamics, anchoring the bar, setting the gravitational floor of the whole system, is the same mass that was there 20 galactic orbits ago, 40. Perhaps more, 4 million solar masses, accumulated over billions of years, sitting at the bottom of the potential well, doing what mass does, holding all the stars in their slow particular paths. I came to this material expecting to find a story about a single dramatic object, a black hole at the centre of a galaxy, impressive in isolation. What I found instead is something more like an argument about embeddedness, about how nothing in a galaxy is truly separate from anything else. The stars in the outer arms are responding to the same gravitational logic that governs S2's 16-year orbit. The spiral pattern is shaped partly by the same central mass that bends the light of stars falling toward the event horizon. The bar exists because of instabilities that the central mass concentration influences. The central molecular zone has the structure it has because of the tidal field of the black hole, and Earth's 225 million-year orbit is one of hundreds of billions of orbits, all organised by the same underlying gravitational architecture. The galaxy is one object. It has parts, arms, bulge, bar, halo, centre, but they are not separate. They are regions of a single system that has been evolving continuously since before the Sun existed. Sagittarius A star is at the center of that system, not the most massive part of it, not the most energetically dominant part of it, not currently, but the center, the point around which the structure is organized, the anchor of the bar, the bottom of the well. Outside this window it is late, the kind of late where the neighborhood has gone entirely quiet and the only light is whatever the sky gives back. I've been sitting with this for a while, the galaxy as one connected thing, the black hole as its organizational center, the structure as something that accumulated rather than was designed. And what strikes me isn't the scale. The scale is just numbers. What strikes me is the patience of it. Billions of years of force applied continuously, and the result is a shape. A coherent, recognizable shape with arms and a bar and a center. The center has been there the whole time. What is going to happen to it? What is approaching the center from the outer galaxy? What will eventually wake the dormant thing at its heart? And what that waking will mean for the structure it has spent billions of years helping to build? That is where this is going next. Something is coming. Not toward Earth specifically, toward the galaxy, toward the gravitational center of it. The Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a current distance of roughly 160,000 light-years, is on a trajectory that will bring it into direct collision with the Milky Way in approximately 2.4 billion years. The timing is uncertain. Orbital mechanics at galactic scales involves enough unknowns that the estimate carries a real margin. But the direction of travel is not seriously disputed. The LMC is approaching, has been approaching, is, at this moment, already doing the slow gravitational work of distorting the Milky Way's outer halo with its mass. The collision won't look like a collision in any ordinary sense. Galaxies are mostly empty space. The stars won't smash into each other. The gas clouds will interact, compress, trigger star formation in bursts across both systems. The LMC will be disrupted, pulled apart by tidal forces, its mass gradually incorporated into the Milky Way over hundreds of millions of years. What had been a satellite galaxy will become material, and a significant fraction of that material, gas, stellar debris, the diffuse stuff of a disrupted galaxy, will find its way eventually toward the center of the Milky Way, toward Sagittarius, a star. This is what wakes a black hole, not drama, not a switch, just material arriving at the event horizon in quantity sufficient to raise the accretion rate above the threshold where the energy output becomes significant. The physics is straightforward. More mass falling in means more gravitational energy released, means more radiation emitted, means the object transitions from its current low luminosity state towards something brighter. How much brighter depends on how much material arrives and how efficiently the accretion process converts in-falling mass to radiation, a parameter that varies and is not trivially predictable. Current estimates suggest Sagittarius A star could grow by a factor of roughly 8 in mass during the LMC collision event, 8 times its current mass, 32 million solar masses give or take, sitting at the center of a merged and restructured galaxy. The accretion rate during the peak of the event could approach or exceed what Esca A was doing during its active AGN phase 2.6 million years ago. The same phase that inflated the Fermi bubbles, that delivered elevated X-ray flux to the upper atmosphere of early Earth, that left structures still visible and still expanding in the galactic halo today. All of that, again, possibly more intense, 2.4 billion years. I want to say something honest about that number, which is that it produces in me a specific cognitive sensation for which I don't have a precise word. It's not that the number is too large to think about. I can think about it in a technical sense. I can place it in context. 2.4 billion years ago, the most complex life on Earth was single-celled. Eukaryotes had only recently appeared. The oxygen in the atmosphere was still building toward levels that could support complex animal life. The whole of multicellular existence, every plant, every fungus, every animal that has ever lived, fits inside the period between then and now, with room left over. So 2.4 billion years from now is that far again. Forward. A duration in which everything currently alive on Earth, every species, every ecosystem, every geological configuration of the continents will almost certainly be unrecognizable or absent. The sun will be meaningfully brighter, hot enough that liquid water on Earth's surface becomes increasingly difficult to maintain. Whatever is alive, if anything is alive, will be so different from what exists now that the word descendant may be inadequate. And at the center of the galaxy, at that time, Sagittarius A star will be waking up. The number is real. That's what produces the sensation I can't name. Not that it's large, but that it's real. That the physics is already in motion. The LMC is already approaching. The gravitational distortion of the outer Milky Way halo is already measurable. The trajectory is already set within the uncertainties, and 2.4 billion years from now, somewhere in the future of this galaxy, material will begin falling toward the center at a rate that Sagittarius A star hasn't experienced in millions of years. What does it actually mean for Sagittarius A star to be dormant right now in terms of physical state? Not rhetorical, a genuine question worth sitting with. The mass is all there. The event horizon exists unretracted at its current radius. The gravitational field extends outward in every direction, unchanged by the quietness of the accretion, the S-star's orbit. The central molecular zone churns with gas and dust and stellar winds. The accretion flow, the thin, hot, radiatively inefficient structure through which a trickle of material slowly spirals inward, is present and active, just running far below capacity. It is a system in a low-energy configuration, not an off system, not an absent system, a system where the input rate is low and the output is correspondingly minimal, the way a fire that is almost out still has structure, still has heat at its center, still has the capacity to catch if fuel arrives. The potential is structural. It doesn't evaporate during quiet periods. It waits, in a completely physical, non-metaphorical sense, for conditions to change. The LMC collision will change conditions. There's a detail in the research that I keep returning to, not because it changes the picture significantly, but because it adds a specific texture to it. The distortion of the Milky Way's outer halo by the LMC is already happening, not in the future now. The Milky Way's dark matter halo is not a perfect sphere. It has a wake behind where the LMC is passing through it, a gravitational wake, a slight overdensity trailing the LMC's orbit through the halo. This wake is detectable. Astronomers have measured it. The LMC is, right now, already doing gravitational work on the Milky Way at large scales. And the Milky Way's disk, including the Sun, including this solar system, is responding. Not dramatically. The disk is slightly offset from the true center of the dark matter halo, pulled by the LMC's mass in a way that produces a measurable drift. The whole disk, moving. The Sun is not orbiting quite where it would be orbiting if the LMC weren't there. The perturbation is small, genuinely small, not something that affects anything on human timescales. But it is real, and it is happening now. The future collision has already begun, in the only sense in which any gravitational event begins, gradually, at the largest scales, through the slow accumulation of influence. I've been trying to find the right way to hold the future scenario. The waking of S-Gray star, the eruption of new Fermi-scale bubbles, the restructuring of the inner galaxy, without tipping into either alarm or false comfort. The honest position seems to be something like, this is a real event, in the future of this galaxy, governed by physics that is already operating. Earth will almost certainly not exist in any recognizable form by then. This sun will be in its final stages. Whatever the event means, it doesn't mean anything for the current inhabitants of this planet. And yet the event is already set up. The LMC is already on its trajectory. Sagittarius A star is already sitting at the center, dormant, a 4 million solar mass reservoir of gravitational potential waiting for material. The chain of causation that will eventually deliver that material to the event horizon is already partly in motion. The physics doesn't require permission or awareness. I find this not disturbing exactly, something else. There's a quality to it that feels like the opposite of urgency, like watching a very slow wave on a very large body of water, knowing where it's going but being so far from its destination that the knowledge produces something closer to stillness than concern. The Andromeda collision is also coming. Roughly 4 to 4.5 billion years from now, Andromeda, the Milky Way's largest neighbour, a galaxy of roughly 1 trillion stars with its own supermassive black hole at the centre, will merge with the Milky Way in an event that will completely restructure both galaxies over hundreds of millions of years. The two central black holes will eventually find each other, spiral together, and merge in a burst of gravitational wave energy detectable across enormous cosmic distances. The resulting black hole will be far more massive than either current one. The LMC collision is a prelude to that. A smaller disruption, earlier, delivering new material to a center that is already preparing, structurally, physically, through the slow accumulation of approaching mass, for an event on a far larger scale. All of this is already in the future of this galaxy. The trajectories are set. The physics is operating. The dormant thing at the center is waiting, in the way that physical systems wait, not consciously, not with awareness, but with full retention of every physical property that defines its capacity. What wakes a black hole is simple. Material. More of it than the system has been receiving. A threshold crossed, not dramatically but continuously, until the accretion rate climbs and the output climbs with it, and the quiet thing at the center of the galaxy begins doing what it did 2.6 million years ago, pushing energy outward, inflating new structures, altering the environment of everything near enough to be affected. 2.4 billion years. The number sits there, real, unhurried, already in motion. What the next part of this returns to is something smaller, not the future but the number itself, the mass, the 4 million solar masses that have been present through every chapter of this, sitting at the center, organizing everything around it without requiring any active state to do so. The number hasn't changed since chapter 2, but everything around it has filled in, and the number is different now for that reason, even though the number is the same. The number was 4 million solar masses. It still is. That's the first thing to say. Nothing about the number has changed. Sagittarius. A star contains the same mass it contained when the chapter that named it first put the figure down, and the same mass it had when the S-stars were first tracked, and the same mass within a rounding error that is itself measured in thousands of solar masses that it has had for millions of years. The number is stable, The object is stable, 4 million solar masses, compressed inside a sphere that fits within Mercury's orbit, sitting at the centre of the galaxy at a distance of 26,000 light-years. Same number, entirely. And yet, there's a thing that happens to facts when you spend time with them. Not a corruption. The fact doesn't change, the accuracy doesn't degrade. It's more that the fact acquires neighbours. Context arrives around it the way furniture arrives in an empty room. The room is the same room, the dimensions haven't changed, but with the furniture present, the space feels different. You move through it differently. You understand, having walked around in it, what the room actually is. 4 million solar masses was an empty room in Chapter 2. The number was accurate but unaccompanied. Compared to Mercury's orbit, compared to the notation required to write it in kilograms, compared to a few star clusters and a brief mention of density, and still, mostly empty. A very large number sitting in a space that had nothing yet to give it company. Now the room has things in it. S2, completing its 16-year ellipse at 7,650 kilometers per second, the orbit precessing slightly with each pass in a way that Newton alone cannot account for. The Fermi bubbles still expanding outward through the galactic halo, carrying the energy of an active period that ended roughly 2.5 million years ago. The ozone layer, 2.6 million years ago, receiving elevated UV as a consequence of something happening 26,000 light-years away. The spiral arms, shaped partly by the gravitational dynamics of a centre that has been present for the entire lifetime of the galaxy. The LMC approaching, the accretion flow thin and radiatively inefficient, delivering a few hundredths of an Earth mass per year to an event horizon that sits and receives it without drama. The number is the same. The room is not empty anymore. I want to try something that might not work. I want to hold the number, 4 million solar masses, and ask what it feels like now compared to Chapter 2, and whether the feeling has changed in a way that tells us something real, or just something psychological. The honest answer is both. The psychological change is real, something that has been encountered in context, lived with across multiple chapters, placed in relation to other things, does feel different from something encountered as an isolated datum. That's not a flaw in how we process information. That's how understanding actually works. Facts in isolation are inert. Facts in relation are knowledge. The 4 million solar masses sitting next to the Fermi bubbles, next to S2's orbital velocity, next to the approaching LMC, next to the thin ozone layer of 2.6 million years ago, that 4 million solar masses is doing cognitive work the isolated number could not do. The real change is also there, though. The number is the same, but what it is a number of has become more specific. In Chapter 2, 4 million solar masses was a mass. Full stop. By now, it is the mass of a specific object with a specific history, an object that was active and then quieted, that produced structures still visible in the halo, that holds the galactic bar in its current configuration, that is being approached by material that will wake it in 2.4 billion years. The number refers to something with texture now, with duration, with consequence. Mass, in physics, is not just quantity. It is the source of gravity, the shaper of space-time geometry, the thing that determines how long orbits take and how fast material falls and what structures form in what configurations around what centres. 4 million solar masses isn't just heavy. It is gravitationally consequential in specific ways that have played out across billions of years and that will continue playing out for billions more. The mass is the same. What the mass does, what it has done, is now visible in a way it wasn't at the beginning. The event horizon, 12 million kilometers radius, 25 million kilometers diameter, still fitting inside Mercury's orbit, same as it did when that comparison was first made. The comparison hasn't improved with repetition. Mercury's orbit is still an abstract quantity for most purposes, but the event horizon now sits at the center of a lot of other things: the S-star cluster orbiting it, the accretion flow feeding it at a trickle, the jets that erupted from its vicinity 2.6 million years ago and are still moving outward, the bar of the galaxy oriented around the gravitational center it marks, the approaching LMC that will eventually deliver new material to it. The sphere of no return, 25 million kilometers across, doing very little right now, very little. Not nothing. The distinction mattered in Chapter 3, and it matters here too. A few hundredths of an Earth mass per year crossing the event horizon. Infrared and X-ray flares occurring several times daily, each one monitored by instruments on a planet 26,000 light-years away. The accretion flow present, active, inefficient but real. The gravitational influence extending outward in every direction at the speed determined by general relativity. Changes in the gravitational field propagate at the speed of light. So in a sense, the gravitational state of Sagittarius, a star right now, won't be felt at Earth's distance for another 26,000 years. We are feeling right now the gravitational state of Sagittarius A as it was 26,000 years ago, during the Upper Paleolithic, when humans were making cave paintings in what is now France and Spain. I almost made a point of that and then pulled back, because the point risks becoming something it isn't. The gravitational influence of Sagittarius A star 26,000 years ago and right now is, for all practical purposes, identical. The mass doesn't change on those timescales, and the gravitational field of a stable mass doesn't change either. The light travel time delay is real, but produces no detectable difference in the gravitational environment here. It's a true fact that does less work than it initially seems to, but I find it difficult to let go of entirely. Something about it sits with me. The gravitational field we're inside right now was emitted, if emitted is even the right word for how gravity propagates, during a period when our species was painting animals on cave walls in firelight. The field left the galactic center when that was happening and arrived here now. We are, in the most technical sense, receiving a 26,000-year-old gravitational message. That's not meaningful in any scientific sense. I know that. It's just true. How massive is massive? The question in the title hasn't been answered, and it isn't going to be. Not because the answer is unavailable. The answer is 4.297 million solar masses, plus or minus about 12,000, but because the question is asking something the number alone can't answer. How massive is a question about relation, about where the mass sits in the context of everything around it. And that context has been the whole project, massive enough to hold the S-stars in 16-year orbits at velocities that require relativistic corrections, massive enough that during its active phase, its X-ray output reached the upper atmosphere of a planet 26,000 light-years away and left a chemical trace in the ozone layer, massive enough to anchor the bar of a spiral galaxy that spans 100,000 light-years, massive enough to be woken, eventually, gradually, by the approach of a satellite galaxy that is itself hundreds of millions of solar masses, massive enough that the structures produced by its active past are still expanding outward right now and will continue expanding for hundreds of millions of years before they diffuse into the halo and become invisible. That massive, not a number, a set of consequences. The room is not empty anymore. That's what this chapter is really trying to say, has been saying in various ways since the first paragraph. The number is unchanged and the room is completely different, and both of those things are true simultaneously, and neither one undermines the other. 4 million solar masses, sitting at the centre of the galaxy, in a dormant state that is not absence, holding the whole slow-rotating structure in place the way foundations hold buildings, not through active intervention, just through being there, being massive, having been there long enough that everything else has organised itself around that presence. The mass is the same, and that, after everything, feels like enough. Right now, not as metaphor, not as approximation, but as literal statement of physical fact, Sagittarius. A star is at the centre of the Milky Way. The accretion flow is present, thin, hot, inefficient, delivering its few hundredths of an Earth mass per year to the event horizon, with the unhurried regularity of a process that has been running in some form for billions of years. The S-stars are moving. S2 is somewhere in its orbit, past periapsis now, moving outwards along the elongated ellipse that takes it from 120 astronomical units at a closest approach to roughly 10 light days at its farthest, and then back again, same path, same velocities, same relativistic corrections applied by the geometry of the space-time it moves through. The central molecular zone is turbulent and dense. The magnetic fields in the innermost parsec are extreme. Young massive stars orbit within fractions of a light-year of the event horizon, burning fast, shedding stellar wind into the surrounding environment. Some of that wind captured, some blown outward, the balance feeding the thin accretion that keeps grey star in its current low luminosity state. All of this is happening now, not in a textbook, not as a model, as an actual physical situation, occurring in real time 26,000 light-years from here. The Fermi bubbles are still expanding. This is the detail that stays with me most, for reasons I haven't fully worked out. The jets that produced them switched off, by current estimates, around 2.5 million years ago. The active phase ended. Sagittarius. A star quieted, and the structures that phase produced have been moving outward ever since, carrying the energy of that period through the galactic halo at hundreds of kilometers per second. They are not slowing in any way that is currently measurable. They are still warm with the memory of it, still glowing faintly in X-rays, still emitting in gamma rays, still pushing the halo gas ahead of them in a slow, enormous wave that began before the genus Homo existed and will continue long after. Long after what exactly? The sentence doesn't have a natural completion. Long after. The Erosita bubbles are larger still, extending 45,000 to 50,000 light-years above and below the galactic plane, still moving, still carrying the imprint of whatever activity produced them. The nested structures, Fermi inside Erosita, both centered on the galactic center, both roughly symmetric, both still in motion, are one of the most visually striking things in the Milky Way if you have eyes capable of seeing in X-rays and gamma rays, which nothing alive on this planet does. But the structures are real regardless of whether they are perceived. They move through the halo. They alter the circumgalactic medium. They will continue doing so for hundreds of millions of years before they diffuse completely into the background. The background itself, the hot, diffuse gas of the galactic halo, will absorb them. Eventually. Everything eventually. But not yet. The LMC is still approaching, 160,000 light-years away, moving along a trajectory that will bring it into the Milky Way in 2.4 billion years. Its gravitational wake is already measurable in the dark matter halo. The Milky Way's disk is already slightly displaced from the true center of its dark matter distribution, pulled by the LMC's mass in a way that produces a real, measured drift. The approach has already begun at the scale where gravitational events begin, gradually, silently in the outermost reaches of things, and Sagittarius, a star, is still at the centre. Waiting is the wrong word. It implies awareness of what's coming, and there is no awareness, only physics. But the physical state is one of readiness in a structural sense, a reservoir, a low-energy configuration with full retention of the capacity for a higher one. The mass is all there. The event horizon is all there. The accretion machinery is present, running below capacity, available to be driven harder when harder driving becomes available. The conditions for waking are being assembled, slowly at galactic scales, without urgency, without awareness, without any of the qualities we associate with anticipation. Just the physics, just the approach. I keep thinking about the cave paintings. Not as a meaningful comparison. I said in an earlier chapter that the light travel time fact does less scientific work than it seems to, and that's still true. But the gravitational field we're inside right now, the field from Asia A, arriving after 26,000 years of travel, left the galactic centre when humans were painting aurochs and horses on cave walls by firelight. The field left then. It arrived here now. We are in it. It is shaping fractionally the orbit of the planet we're on. The people who painted those animals had no knowledge of Sagittarius, a star, had no concept of galaxies, of black holes, of the galactic centre or its mass or its history. They painted what they saw. They slept under a sky. They couldn't read the way we read it now. And the gravitational field that passed through them, through their caves, through their fires, was the same field passing through here tonight. That's not meaning. I keep having to remind myself of that. It's not meaning, it's just continuity. An unbroken physical thread running from the galactic centre through 26,000 years of human history to this room, this hour, this particular quiet. Sagittarius. A star will produce a flare tonight, probably several, small ones, infrared brightness, bumping upward by a factor of a few for minutes or hours, then settling back. Somewhere right now a telescope is pointed at the galactic centre, recording the light from the region around the event horizon, watching for the variations that reveal the structure of the accretion flow. The data is being collected. It will be analysed. The flare, when it comes, if it hasn't come already, will be logged, catalogued, added to the decades-long record of Stuart A star's variability that has been building since astronomers first resolved the radio source in 1974. The telescope is doing its patient work, the black hole is doing its patient work. The distance between them and 26,000 light-years of gas and dust and scattered stars is doing nothing at all, just existing, just being the distance it is. To everyone who has been here for this, listening, returning, making this kind of space possible, thank you. This project runs on its own, self-funded, and it exists because of people on Patreon who believe something like this is worth keeping alive. Alison, who has been here the longest, thank you. Matthew M. Brian Winter, thank you both. And to everyone else who supports this work quietly, in the background, without whom none of this would continue, this is for you always. There is something at the centre of the galaxy, not a metaphor, an actual object. 4 million solar masses compressed inside a sphere smaller than Mercury's orbit, sitting at the rotational heart of the Milky Way, holding the S-stars in their tight ellipses, anchoring the bar, producing its faint irregular flickers in the dark, waiting, in the only way a physical system waits, for conditions to change. It has been there longer than the sun. It is there right now, the centre, still.